Hi everyone, and welcome back to Physics 2A lecture. We're going to go ahead and get started this week through the idea of oscillatory motion and waves. So a bit of an introduction into what oscillations are. When we have an oscillation, it's some type of object that moves back and forth between 2 points. So let me go ahead and give you guys an idea of this. That'd be something like a spring, okay, that say you pull it apart, okay? When you pull it apart, it'll come back together and oscillate. It'll go back and forth between these 2 points, okay? So that is an idea of an oscillation, and this involves some type of force and an energy, okay? And through these oscillations, waves are created. Okay, so if you think about water, and when you drop, say, a pebble in it or a rock into water, it'll create these little ripples in the water. And that is because of these oscillations. And this is an idea of waves as well. And these waves are any disturbance that moves from its source and carries some kind of energy. Okay, an example of waves and things that have oscillatory motion, that's going to be water, earthquakes, visible light, electrons, and so forth. So we're going to look at this in more detail and hopefully be able to describe this motion through physics. So the first idea that we need to understand is Hooke's law, and that is also going to be involved with stress and strain. So let's go ahead and first look at Newton's first law. Okay, remember that in Newton's first law, we know that some kind of object will be experiencing forces. And in this case, an object that oscillates back and forth is also experiencing forces, okay? And say we have some kind of ruler, okay, a plastic ruler that can easily bend. If we move it from its equilibrium position, we can say, or its starting position, just where it's like at rest, up and down, and we move it either to the left or the right side and let it go, it will oscillate back and forth between these 2 points, okay? Now, why is it doing that, or how is it doing that? That is going to be something called a restoring force, okay? That restoring force causes an object to return to a stable equilibrium, or where the net force is 0. So we've got this plastic ruler and we displaced it by some distance, right? Well, now it wants to be pushed back to its equilibrium position. That's where it wants to be. Objects want to be at equilibrium. So what happens is this restoring force tries to push it back to that equilibrium position. Okay, so then we get this back and forth motion, and then eventually it goes back to equilibrium. Okay, and Hooke's law is what can describe that force. Okay, so Hooke's law states that the restoring force F is equal to the negative constant K that is related to the difficulty in deforming the system times the displacement from the equilibrium, or the deformation, okay? So again, the restoring force is equal to negative this constant, okay, and that's related to the difficulty in deforming the system, times the displacement from the equilibrium, okay? All right. So a bit more on that. The force constant K here is related to the rigidity or stiffness of the system. So how hard is it to move? And larger that force constant, if we increase this guy, the greater the restoring force, okay? Which means the stiffer the system, okay? So we've got a few examples here on what it kind of looks like. Our equilibrium position is, of course, just straight up and down, okay? And there's just some forces involved if we push it this way, or I'm sorry, if we move the ruler from equilibrium like it has here, okay, our restoring force is going to be in the opposite direction, okay, and it'll have some velocity and so forth, okay. One thing that I should note are the units of this constant are Newton per meter. Okay? All right, moving right along, we're going to go ahead and get into an example. So this example states how stiff are car springs. What is the force constant for the suspension system of a car that settles 1.20 centimeters when an 80 kilogram person gets in? Okay, so again, we're looking for the force constant. Okay, so we just learned from Hooke's law that F equals negative kx. Okay, now if we want to know the force constant, that is going to be solving for k. Okay, so k is going to be equal to negative F over x, using a bit of algebra, okay? And we do need to note that in this case, we have a car that settles for at a distance or displacement of 1.2 centimeters, okay? So this term settles, when something settles, it kind of I guess you could say just goes in the negative direction, right? It just settles down, I would say. So we need to note that this is going to be negative, okay? So we have our negative force, which is actually going to be our mg, right? That's the force of the person, divided by our x, okay? So if we plug this stuff in, we get a negative 80 kilograms times our 9.8 meters per second squared, divided by x, which is going to be negative, and this is in centimeters, so we need to convert that to meters, okay? So if we want to do that, we can say 1.2 centimeters. How many centimeters in a meter? 100. Okay? So then we get that our constant here is going to be what? Let's go ahead and use our calculators. 80 times 9.8 divided by 1.2 divided by 100. And be careful when putting this into your calculator. Make sure that you have all of your parentheses and such, because it can get very confusing very fast, okay? So 0.012, that's how many meters, and I get that my force constant is 6.53, and times 10 to the fourth. And remember, our units are Newton per meter. Okay? All right, so that is my force constant for this suspension system of a car. Okay, so let's go ahead and move on from this example to the idea of energy in Hooke's law of deformation. Okay, now work has to be done to produce some kind of deformation in a system, and this means that a force must be exerted through a distance. Okay, remember that work is equal to force times some kind of distance. Okay, And we want to note a couple things before moving this or changing this into the idea of oscillatory motion. So an elastic potential energy, we need to note, is equal to 1/2 kx squared. Okay, remember from a spring, we looked at the energy of a spring in the past. So this is the potential energy of a spring. Okay, that's the elastic potential energy. And so the work done in deforming a system is actually very similar. Okay, and that's because work is equal to our applied force, okay, times some distance here. Now our force due to an elastic force is going to be 1/2 kx, and then our distance is x. So notice that our work done is similar to our elastic potential energy. Okay, now let's go ahead and look at an example here. So we are calculating stored energy in a tranquilizer gun spring. Okay, so we're going to go ahead and answer these couple questions. How much energy is stored in the spring of a tranquilizer gun that has a force constant, of 50 Newton per meter and is compressed 0.15 meters? Okay, so again, we're looking for our energy. So our energy, our potential energy, or our energy, is 1/2 kx squared, right? We just learned that. So we're going to go ahead and plug this in. 1/2 times k, which is 50 newtons per meter, times x, 0.15 meters squared. Okay, so again, it's compressed, so it is, that's the distance. Okay, so let's go ahead and plug that into our calculator. 0.5 times 50 times 0.15 squared. And that gives me an energy that's actually pretty low, 0.563 joules. Okay, remember that energy is in joules. Okay. Now, again, this is for part A. Now, if I'm looking at part B, if you neglect friction and the mass of the spring, at what speed will a 2-gram projectile be ejected from the gun? Okay, so let's stop and think about this for a second. Okay, so my potential energy is, my elastic potential energy, I should say, EL, is going to be the same as when that kinetic energy is released from the barrel of that tranquilizer. Okay, so here's an example or the illustration that came with this problem. So we have the tranquilizer gun and the spring gets compressed. There's some kind of work done. And then as that spring is released, that's what the kinetic energy is going to be out of the gun. Okay, so again, this potential energy is going to equal my kinetic energy as it's released. So this means that this number, 0.563 joules, is equal to that 1/2 mv squared. Remember, we learned that this is the kinetic energy. Okay, so our velocity then is going to be this number, 0.563 joules times 2 divided by our mass, which was given as 2 grams. So I'm going to go ahead and put 2 grams, but then we need it in kilograms. So we need to say 1,000 grams, per kilogram, and then square root that. And we should get 23.7 meters per second. So that is our velocity of that projectile being ejected. Now look for the next video to continue the lecture.